Hello everyone, Juan Fraire here again. I put together a second video to summarize and discuss a little the latest approach that Scott proposed for the contact graph routing, and then I will discuss a second option I've been thinking about. So Scott approach and also the second one I will discuss also use a single entry per neighbor node in the root list, which gets updated as required, so basically as time goes by. So every time that a root which is in the root list to D, for example, in this example, it in the past becomes to be in the past. So basically there is the to time of the root is reached. This entry is updated, and so every time, all the time, we have a valid route to a given destination through each of the neighbor node if it exists in the contact graph. So I propose a little contact graph here as an example with a node A that wants to reach node D. There are two first hop contact to, in this case, only neighbor, which is node B. Through contact number 1, we can reach contact 3, 4, 5, and 6 to reach D. And through contact number 2, which is farther ahead on time, we can reach node D using contact number 6. So Scott approach that is based on replace the root on to time event works like this. In the beginning, at time 0, I ran the extra search to get a root, which in this case would be the best root, would be 120 seconds, minutes, whatever unit metric this number could be. Then I will add this entry to the road list to D through neighbor B. So I have 120 of best delivery time, and this route has a volume of 10 time units, whichever the data rate we're using in this node. So I will able to reach node D with a volume of 10 using this route. As time goes by, this route will be in the root list to node D until time 100. Time 100 is the time at which this path is no longer valid because it becomes on the path. So at time 100, the limiting contact will end, and the limiting contact is the contact that actually is the first contact in terminating in all the path. And this event of reaching time 100 will trigger a new route calculation to replace or repair the node B in the road list. This calculation will render an alternate route through another contact to node B, which is the contact number 2. And this contact will replace will replace the previously calculated route with the best delivery time of 300 in this case, and with a volume of 10 again. In this example, contact number 6 has only a volume of 10, so which is the smallest capacity contact with capacity 10 in all the path. The same happened in the previous calculated path from in contact 3, 4, and 5, all of them with a capacity of 10. In this case, the route will be in the list until time 300, which is the to time of this route, and also the end time of the limiting contact, which is contact number 2. The problem, or maybe not the problem, but the property of this approach is that obviously not all contacts are explored. This is because if subsequent contacts, non-local but remote contacts now, can reach the node destination D with a worse delivery time than the first one found, they will not be explored. So this is not a problem for if we only account for best delivery time. If we do always want to have the route list updated with path with a best delivery time, this method is correct and will always guarantee that the route list to D is populated with entries, which provides the best delivery time through all local contacts to neighbor B in this case. However, if we start taking into account the volume that characterize this path that we found, this approach is not accurate because in this example it is clearly seen that the path through contact number 3 has a volume of 10. However, the contact A to B, the first one, which is contact number 1, actually is able to allocate a total volume of 30 units using also contact 4 and contact number 5. So the volume calculation in this entry is not real in this case. However, the best delivery time is 120 in the first place, and will be that, and that's accurate, and that works. So I think that the replace on two-time approach, is accurate if we only account for best delivery time, but it's not enough to make a good calculation of the volume of the data we can send through a given contact. So an alternative to overcome this limitation is to also replace routes on depletion, which is depletion would be the situation in which a given path has no more capacity to be allocated to a given traffic. So in this alternate approach, a path in the route list is replaced not only when the two-time arrives, but also when a depletion happens in forwarding time. So given the same contact graph, this would work something like this. Initially, at time 0, we find the best route with a best delivery time of 120. There is a mistake there in the slide. And with a volume of 10. And this is equal in both approaches. And this route will be in the list until time 100, which is the two-time as well, or when the routes get depleted. And the routes get depleted when I forward as many packets or as many bundles, just to overbook all the capacity that this path has. So for example, in this case, will be 10, which is the volume that we calculated through this path. So if we send as many data to reach a volume of 10, then there is a limiting contact in terms of volume here that get depleted. In this case, is contact number 2. So this, in this case, would trigger a new route calculation because this path is no longer valid, even though the packet might not follow this route afterwards. Maybe node B will find a different path for this bundle. Anyway, it's a good guess of what the capacity through B is going to be, in this case through contact number 1. So so if depleted before 100, so in this case this path got depleted before time 100, a new Dijkstra is calculated. And in this case, so a new Dijkstra finds the route through contact number 4, which also has a volume of 10 and a slightly higher best delivery time. And so this is like the new entry to route D, which can eventually again get depleted if I use this capacity 10. So something to notice here is that this calculation will only be triggered if this capacity is consumed, if this volume is consumed in the forwarding phase. So if this gets depleted, we again go for another route calculation, which will find another path through node 5, and which can eventually again be depleted. This best delivery time is now 160, and therefore after these 3 phases we were able to allocate a total capacity of 30 units to destination D through contact number 1 to node B. Something interesting to note here is that if we use the previous approach, which doesn't account for the volume, we are forwarding would just forward as many packets as possible until time 100 that the route gets replaced to node B. So eventually, in a given traffic situation, this could imply that we could be sending 100 volume to node B when node B actually can only physically deliver to node D a total of 30. So the replace on two time approach, which is the previous one, in theory, will be more congestion prone than this approach. So in this case, next step is another route calculation is made, which is in this case is exactly the same as the second route calculation in the previous example, which could find another route through node to contact 2 and through contact 6 to reach D again, with a volume of 10 in this case as well. So in this contact graph, we could be able to allocate a total of 40 units to node D, even though the first contact 1 and 2 have a total capacity of 200 in total. So this approach is a little bit less optimistic on the best delivery time, because as we replace routes, because depletion happens, the best delivery time will eventually increase in relation with the previous approach, and this increase is because we are actually using and consuming volume of contacts. So as we overbook contacts, we will need to use others, and these other contacts will eventually have a higher best delivery time. So this is less optimistic regarding the previous approach. In some extent, it could be more realistic, and it's also more accurate in the volume estimation, as we see, because we calculate every path as required, if required by the forwarding stage. The problem is, obviously, we will be using more distance searches, and we will need to use also a local track of each contact residual volume, which is not a big deal in a data structure. However, the good thing about we use more Dijkstra searches is that we use it only when a lot of forwarding is happening, when the forwarding requires. So in this case, if we wouldn't have data to node B, for example, we wouldn't be triggering these subsequent Dijkstra searches. It will improve congestion management from a local perspective. We, as noticed, we are only using the information in the contact graph to make these forwarding and routing decisions, so we are not relying on feedback messages. However, if such messages could be present, such as in estimated capacity consumption, which is one of the approaches proposed by Rain, and I think there are other similar approaches proposed by other people. Those feedback messages could be just directly used to update the local capacity view of volume view of the contact graph. However, if not present, this would even improve the congestion management capability of the previous approach. So, and something important to notice as well is that if we use this approach, we could use subsequent Dijkstra searches that won't repeat the previous calculations if the volume of the contact is considered. Therefore, this implies that no k-shortest path algorithm such as Yen will be required either. So all routes will be calculated and discovered by demand, as we previously said, as the traffic is being forwarded. So, well, this I think that we still need to revise this more and discuss it more, but I just wanted to share this perspective and this view. It's very easy. It's more easy to show this graphically and than by text. So, well, this is just to complement my last email. And well, thank you, and let's keep going on this discussion.